What's going on, everybody? This is Mr. Diamond, turning the volume down slightly because I had to turn it up earlier. But we're going to be going through our Section 4 notes, acids and solution equilibriums. Now, ideally, we would spend quite a bit more time on this, and there would be quite a bit of other things that we could go over related to this. But due to, everything that's going on in the world right now, we're not going to be able to do that. So I'm going to kind of do a little bit of an amended version of what these notes would be. So technically, we've been talking about KEQ. That's actually a general constant for equilibrium. In fact, usually what we would have been using and what a lot of places seem to be using now that I've done more research on it is Kc. KEQ is what I've learned, and KEQ is what a lot of other places learned or used when I was in college. But Kc is actually a specific version. That's concentration equilibriums. It's whenever you're just changing the concentration of reactants and products as something progresses. But there's actually more than one type of KEQ. Kc is for concentrations, but there's Ksp, which stands for basically solution product equilibrium. Sp is for solution product. And then Ka is for acidic equilibrium. So Ksp is for solutions, Kc is for concentrations, and Ka is for acids or acids and bases. Well, technically it's for acids. It would be Kb for bases, but we're not going to go into that detail here. So Ka is the acid ionization constant. It is the equilibrium constant for the ionization of an acid. So generally speaking, A just represents a piece that's attached. It could be chlorine, it could be nitrogen, it could be phosphate, it could be whatever. But you have H, some number of H's attached to that acid component, plus water, and then you'll get H3O plus, and you'll get A minus. And this is all happening inside of water. And because it's happening in water, we get to ignore the H2O as part of this. And so we're really only going to be considering HA, H3O plus, and A minus. Now, H3O plus is used when you specifically list the equation involving water. Some places, and sometimes I might do it without thinking about it, sometimes they'll just ignore the water and you'll know that it's happening in water. And they'll just do HA gives reversibly H plus A minus, but they mean the same thing. So don't get that confused if you see H3O plus or H plus concentrations. They mean the same thing. It's just that H plus could be reacting with water if it's in water, and if it's an acid, it's in water. Now, the biggest change here is something I believe you should have talked about in your previous classes. Don't quote me on that, but the strength of acids, I think you guys had kind of mentioned you'd already talked about. When we refer to an acid as strong or weak, it means something different than what most non-scientific people think. When most people think about it's a strong acid, they probably think it'll melt your face off. Oh, it's a weak acid? Oh, it's probably, safe. But as I try to instill in my general chemistry kids, you can have a strong acid that you can fill a swimming pool with and you could swim around in, and you could have a weak acid that will burn your face off. The actual damage it does to your body is based on concentration, not strength. Strong acids just mean that they ionize completely in water. They will completely split apart, and that means we actually have to use a single-headed arrow. So if you've gotten in the habit of always using a double-headed arrow, one of these things down here, you actually can't do that for acids. If it's a strong acid, you get to just do one normal arrow. And if it's a weak acid, it ionizes only partially, which means it is reversible. It can go back. And so you have to use if I move my laser pointer out so it comes back, you have to use the double-headed arrow, the right and left-headed arrow, because it is reversible. Now, for weak acids, you basically just do everything the same way we're doing. In fact, we've done a calculation involving a weak acid. It was the one that involved, I believe it was acetic acid in an earlier section. That was actually using a Ka. We just generalized it as a KEQ. The major change for us, though, is that we can involve pHs, pOHs, and stuff like that. So just for reference, because I think this was one of the things that not a lot of you said you recognized, to find pH, you just do the negative log of the concentration of H plus or of H3O plus. Remember, those can be the same as each other. If you know one, you know the other one. pOH is negative log of OH minus. If you multiply H plus and OH minus, you should get 1.0 times 10 to the negative 14th. And if you add pH and pOH together, you should get 14. So using this information, you can solve for basically whatever it is you're actually looking for in the question. You could do an ice table, for example, solve for your concentration of H plus at equilibrium, then take that concentration of H plus, do negative log of that concentration, and you'll figure out what pH that substance will actually have. Speaking of which, that's basically what we're doing in this reaction. So this is the first example type we're going to do is what if the Ka for hydrofluoric acid is 0.00071, what is the pH of a 0.50 molar concentration of hydrofluoric acid? So we'll have to use the Ka, use the pH to solve for whatever our pieces are. We'll solve this basically exactly like we did an ice table. The only difference is that once we know a concentration of H+, we'll have to plug it into a pH question. This will be an attached video, though, so you'll be able to see how we work through that one there. Now, for strong acids and bases, they ionize completely. So again, you don't use a double arrow or anything like that. Actually, what you do is you just turn all of your acid into products. That's it. Like, everything that is there disappears and it turns completely into products. So you don't have to do an X or anything like that. Now, the strong acids can vary from location to location. Sometimes some of these are not counted, like HI occasionally isn't counted. Sometimes they'll count other ones as being strong, like a nitrous acid could possibly be considered a sulfurous acid. But like, these are the ones that are pretty much like everywhere we'll say that these are strong acids. Hydrochloric, nitric, sulfuric, hydrobromic, hydroiodic, perchloric, and chloric acid. So we're just going to stick with this list. I would say you have to have these memorized, but I mean, every assignment you can just look at everything because we're all digital at this point. So, I mean, what's the point of me even saying that? So don't worry about having them memorized. You'll obviously be able to access this whenever you take any tests or anything like that. So an example of this would be, we're going to find the pH of 0.001 molar of HCl. Notice there's no Ka because there doesn't need to be one because HCl just completely splits apart. So we'll work that one out together as well, and you'll be able to see how that goes. Now, our final thing is something we're really not going to have time for, but you can actually have multiple Kas. Multiple Kas are involved whenever there's multiple H's being involved, and those H's will actually ionize in stages. So, for example, you could have H2A, which could be like H2SO4, and you would end up with H2A or H2SO4 splitting into HSO4 minus and an H plus, and then that HSO4 minus could split apart into an SO4 2 minus and an H plus. So these each will have their own Kas, but then to actually solve, you would need to add together your H pluses to figure out what its like pH would be or its POH would be. We're not going to do any problems like this. I was really tempted to try to make one of your test questions like this and like throw you guys to the wolves and just see how well you could do it. But we're not going to worry about that. I just want to mention that this exists so that way when you go to college and you start taking other advanced classes that you can kind of see that this is a thing and you'll kind of expect it a little bit. Ka of the first one though is usually going to be it's usually going to be a lot easier to split apart. It's going to be more likely to split apart, and it gets less and less likely as it goes through the process. As a general rule, that doesn't always hold the case, though. Now, KSP is the other type, but it's a just slightly different approach to the types of problems. The process is the same, but the way the questions are worded are usually different. Ksp is the solubility product. It's the product of the molar concentrations of the constituent ions raised to the power of the stoichiometric coefficients in the equilibrium equation. So this is like the exact same thing that we've been talking about. It's the same exact setup as a KEQ. The main difference is that they're used when dealing with precipitates. The solubility product is specifically talking about like things falling out of solution. And if you remember, solids are not included in equilibrium expressions. So anytime a solid's involved, it's technically a KSP equation, but again, you can generalize it as KEQ, but you'll know that it's talking about solids when it's talking about a KSP. The main piece at play with this KSP, though, whenever we're dealing with this, again, is going to actually be a very slight difference in the wording. The uses of KSP problems are figuring out how much stuff can dissolve in a given amount. Like if you know a KSP, you can actually, in theory, backtrack and calculate how many grams of a substance will dissolve in a certain amount of liquid. We could use this, for example, in like our tea experiment that we used. The example we're going to do here, though, is for calcium sulfate. Calcium sulfate is not completely soluble. It will dissolve in water, but it won't dissolve completely. We know that for every 1 liter of water that you have, you could dissolve 0.67 grams at 25 degrees Celsius. So we want to use that information to calculate KSP. And you might think that seems like a weird wording for the question. How would I actually solve this? It's pretty straightforward. You'll be able to see in the example, but the short answer, if you want to try to attempt this on your own, is if you just assume 1 liter, you then have 0.67 grams, and you can then convert grams to moles. You could turn this into a molarity. Once you've got it in a molarity, you're good. You can solve the rest of the problem. And also remember that in the process of dissolving, all of your ions are just going to split apart. So in this case, calcium and sulfate would split, and you'd have Ca2 plus SO4 2 minus. Again, I'm going to work that out with you though, so you don't have to forget about that too much. And with that, we are at the end of our notes for Ka and Ksp. You're going to find these are pretty straightforward. It's just, like I said, slight modifications to the types of problems you've already been doing. This is the last real mathy section that we're going to be doing. We do have one more section of notes that's going to be this bad boy right here. But this section actually doesn't involve any math. It's just a kind of a thing that I'm tacking on here. We would have covered it in a bunch of like labs this chapter, but obviously we don't get to do labs because, you know, I can't ship chemicals to your house. But we'll talk about this as our last section, but this is really the last like type of problems, calculation, stuff like that I'm going to teach you. So I hope that makes sense. Check for the videos of me working at the example problems that will probably be attached to this daily log. I hope you have a great rest of your day, and I hope to see/hear from you soon.